in today's lecture, we are going to consider the longitudinal short period dynamics of an aircraft, how we can find the stability augmentation system. So let me first define the problem. The longitudinal short period dynamics of an aircraft is given by So as we have studied before in our previous course, that longitudinal motion has two different modes. One is the short period, another long period motion. So this different modes we can define based on the eigenvalues of the system matrix. So I'm not going to detail about it. Already we have explained in our previous course. Also in this course we had also some basics how we can define the short period and long period motion of the longitudinal motion dynamics. So the system equation is given in the linear form. So here we are going to control parameters alpha and angle of attack and pitch rate. And the system matrix given to us minus 0.331 minus 2.52 minus 0.38 and state vector delta alpha and delta q, and our D matrix minus 0.027 and minus 2.6, and the only control is elevator deflection. So here, if you notice, we need to design the stability augmentation system, which will help us how we can make the states goes to zero. It's a linear system, and the equilibrium point is quite obvious, 0, 0. And the question is here, the aircraft has short period handling qualities since the based on the eigenvalues of the system, we can define this is basically short period motion dynamic and design stability augmentation system such that the system follows the desired dynamics, short period eigenvalues 2.1 plus minus 2.14i. So this is the problem, and we have to design the stability augmentation system, and we have the desired poles. This is the desired poles. The system should follow these dynamic characteristics. So let's find the solution for this particular problem. From the given system, we can find the augmented matrix. Okay, one more. This problem we have taken from Nelson book. The reference is defined in the course website, the book. So this problem taken from this book. The augmented matrix, we have, since to find ACL, we can find A minus BK transpose. So if K is the Coulomb vector, we can, if we write the BK K transpose, it will be rho vector. The same thing. So here minus 0.33, 1 minus 2.52 minus 0.38. Then we have B matrix minus 0.027 minus 2.6, and we have K matrix K1 and K2. Okay, and if you simplify this expression, the final ACL, this is ACL closed loop. ACL. Why it is closed loop? Because we consider control in the system. And closed loop or the ACL matrix 0.33 plus 0.027 A1, 1 plus 0.027 A2 minus 2.52 plus 2.6 K1, 0.38 plus 2.6 K2. This is the augmented matrix of the closed loop control system. Now we can find the characteristic equation of the closed loop system. We can write SI minus ACL equal to 0. And from this, we can write S is 0, 0 is minus, we can write this matrix, ACL matrix. This is minus 0.33 plus 0.027 A1, 1 plus 0.027 A2, 2.52 plus 2.6 A1 minus 0.38 plus 2.6 K2 equal to 0. And the final characteristic equation or the value of the inside matrices we can write is plus 0.33 minus 0.027 A1 minus 1 minus 0.027 A2, 2.52, 2.6 K1 is plus 0.38 minus 2.6 K2 equal to 0. And the characteristic equation from this equation, the determinant of this matrix you can write x square plus 0.71 minus 0.027 K1 minus 2.6 K2 is plus 2.6. This is 2.65. This is 2.565 minus 2.61 A1 and minus 0.8 A2 equal to 0. And we can write this expression in this form. Okay, this is the basically we can write this is basically the characteristic equation of the closed loop system. Let us define this equation number 1. Now also from the DGR folds, we have the DGR dynamics from DGR folds, the DGR polynomial we can form S minus 2.1 plus 2.14i and s minus 2.1 minus 2.14i equal to 0. And finally, we have s squared plus 4.2s plus 8.98 equal to 0. And let us define this equation 2. Okay. Now comparing equation 1 and 2, we can write 0.721 minus 0.027 K1 minus 2.6 K2 equal to 4.2 and 2.65 minus 2.61 K1 minus 0.8 K2 equal to 8.98. Now, if we solve both the equation, we have here K1 equal to minus 2.03 and K2 equal to minus 1.31. And from this, we can find the control algorithm U, which is nothing but minus K transpose X. And we can write this is K1, K2, and delta alpha, delta Q. Or we can write minus 2.03 minus 1.31 delta alpha, delta Q. And this is nothing but 2.03 del alpha plus 1.31 del Q. So now let's write the code in MATLAB and we see the result. So if you notice carefully, stability augmentation system, nothing but the controller design for the system. And this is the MATLAB code for this example. So if you notice, the dotted line here indicates the basic airplane and the solid line basically augmented airplane, where we have designed the controller. So the system dynamics, system matrix is defined here, and we can find the damp of A, where we can find the omega and damping ratio and the poles. And we can find the system into state space form. And where, if you notice here carefully, we have set the initial conditions of the state 5 into 5, basically 5 radian and 0. And we have here you can find the solution of the X, Y, and T. This is the solution of the different states. And this is the figure. And in the figure, if you notice carefully, if you have the augmented system where we have designed the controller, and over the response, there is less overshoot, undershoot, and it goes straight to the 0 equilibrium point. But in the case of basic airplane, the convergence after 8 seconds, it is not exactly goes to the 0. So here we can say that augmented airplane is performance better compared to the basic airplane. And this is basically, we have designed the stability augmented system for the augmented airplane. Now, we have done this simulation for the second order system. If you notice, we have the system matrix second order system. But if you look the full aircraft dynamics, and like if we consider the longitudinal motion dynamics of the aircraft, the equation is actually fourth order, right? But once the system become to the order of the system increases, it is difficult to solve sometimes numerically. So in that case, we have different methods to solve this kind of problem. So if I write here, if I write as order of the time increases, it is difficult to find the closed loop gains of the closed loop system. Closed loop, we can say, or controlled system. Controlled system. So to avoid this, difficulty, there is another method we can use, which is called Bhaskara method. This is so to avoid, we can use for numerical method. We can say we can use numerical method. One of the numerical methods, it is called Bhaskara method. So here we can find the control gains, or we can say control matrix. Control matrix. We can use simple formula K equal to PW transpose inverse alpha minus A. So here P is the contributed test matrix, W is the triangular matrix, and alpha is the coefficient of the desired polynomial, and A is the coefficient of the open loop system polynomial. So now here we can form the W matrix for W can form as P already we know, right? We can find P easily. So W we can find 1, A1, AN minus 1, 0, 1, AN minus 2, and 0, 0, and this is 1. So we can form the A matrix for Sm plus A1 is n minus 1, A2 is n minus 2, dot, An equal to 0. So, and other than this matrix W, we can find the other terms in this equation easily. This is already we have found before how to find the other parameters in this equation. Let's stop it here. We'll take an example how we can use this method, this numerical method, to solve or to design the control algorithm for the aircraft system. So you'll be considering the longitudinal motion dynamics of the system and how we can design stability augmented system using Bhaskara method. Thank you.